Okay. Now, when the equation is solved, actually is the solution consists of a summation of terms, infinite terms, right? So, so what I've shown it to you, equation for 10, for 11, the values of non-dimensionals atau dimensionless temperature um, for truncated values. So infinite series have many terms, right? So we just consider the first term of the equation. Um, so you can only use this equation um, for specific uh, model of heat transfer system. For example, for 10, for plane wall, cylinder, you use equation for 11, sphere, equation for 12. And you have this constant. The concept here, constant is just a constant, and lambda is another constant because lambda actually is a solution of this equation, right? And you can see the subscript 1 there. So 1 refer to the first term inside the infinite series. Um, and this constant is a function of Biot number only. And these values, A1 values and lambda 1 values, depends on the Biot number as well as their geometries. And then another function here is the zeros or the Bessel functions. And it is used for cylinders, right? And so for when the values of for cylinder, for example, when they uh, at the center lines, right? So the first order um, Bessel function will go to the, will have the value of 1. Right, so I am referring to the large plane wall. As I said before, the coefficient A1 and coefficient lambda 1 is specific to a plane wall, right? In this case. So you have another value of this constant for long cylinder and sphere. But I just remove the column corresponding to that those geometries. So if you know the value of Biot number with the half of the thickness of the large plane wall, then you can determine the value of lambda 1 and A1 and using it to calculate the dimensionless temperature, right? So let's say if you have a Biot number 0.1, which is the criteria for lump system, right? So the value of lambda 1 will be 0.311 and the constant A1 will be 1.0161. Right. Until now, we are looking at the solution of the problem using tabulated data, right? And you're using this tabulated data to calculate the dimensionless temperatures. So the other way is to use a graph, right? This graph is called Hassler chart. Right. So if you look at this, I have shown you another way to obtain the non-dimensionless temperature, right? Using what you call Heisler chart, right? But this Heisler chart cannot be used to determine uh, all location inside the heat transfer system, right? So in order for you to solve any location inside the heat transfer system, you have to complement the mid-plane temperature with the uh, figure 413b, right? So the first figure 4.13a, the mid-plane temperature will tells you the dimensionless temperature at the center of the plane wall, right? I've shown you the model of heat transfer system at the bottom figures. And then if you look at the figure, the vertical line is a dimensionless temperature in logarithmic plot, right? And then we have a Fourier number on the horizontal axis, and the line, the pink color line there is the reciprocal of Biot number, 1 divided by Biot number. So when the system is satisfied, the lump system, the reciprocal Biot number is 100, right? So if we have Biot number less than 0.1, right, the figure does not show you those values. So in this plot at the center here, showing to you the range of reciprocal Biot number is ranging from 0.05 up to 100. Right, and then that's where the center line. And then if you go to the figure on the right, you have the vertical line tells you a dimensionless temperature at any location in the body. And then we have the horizontal line will be the reciprocal Biot number ranging from 0.01 up to 100 in logarithmic profile, logarithmic plot. And then the pink line there showing you the non-dimensionless distance from the center. So does not cover all, but it varies from 0.2, 0.4, 0.6, 8, 9, and 10, right? So if you know about the center line values, then you can using it to calculate the local values of local temperatures. So this plot is based on equation 413. Let's say you don't want to use the plot, the chart, Heisler chart, you can use equation 413. And you need to use the table because in the table we give you the values of lambda as well as the coefficient A. Right, so this fifth edition books that I give you as a reference is not really include all the information. For example, how we can, what is the solution of this equation, the Fourier equation, and what is the way how to calculate, how to you can relate the mid-plane dimensionless temperature with the dimensionless temperature for at any location theta, right? So that is not included in this book, right? But that equation is not being used mainly to solve need, right? The equation, but what you need to do to have is just the the plot and the table in order for you to have the solution of the problem. Now, finally, we look at the way how we can calculate the amount of heat being transferred in the system. I just use the plane wall as examples. So you have an equation for a large plane wall for 17. We can find the ratio of the amount of heat that been transferred into the system. So if you find that the dimensionless temperature at the center, which is theta naught, right, theta zero there, and if that theta zero, which is defined by the T bread body minus T infinity, and when it reaches to the fluid temperature, right, so it becomes zero. So when Q, ratio of Q, amount of heat, divided by the maximum Q that you can calculate using the energy balance, right? So if that one, the value is equal to 1, it means that our system is already reached to the body temperature, fluid temperature. So if you look at the graph there, you can see that there is a temperature. These are given in a logarithmic plot. So you have a vertical line there is the ratio of heat entering the body, right? So that is from zero, from initial values up to maximum when the fluid reach the temperature of the fluid, and at the bottom one is the square of Biot number with the Fourier number. Is range from 10 to minus 5 up to 10 to minus 4, and the pink line there refer to the Biot number ranging from 0.001 up to 5, right? So you can see that the amount of heat is rising, and it will stop at 1 when Q per Q max equal to 1.